Good evening everyone, and welcome to today's worked exam answer video. Today, based on a request from one of my tutees, I am going to cover a free radical substitution question. And in this particular free radical substitution question, we will be looking at how to write initiation, propagation and termination steps, how we write the overall equations for a particular free radical substitution reaction where maybe we are substituting more than one halogen, and then at the end we'll also look a little bit at how chlorine free radicals can decompose the ozone layer and how they act as a catalyst for that. So there's a question at the bottom about how a particular CFC can decompose to form a chlorine free radical, and then on the back there's the question asking for the two equations which shows how that decomposition occurs. So we are having a look at trichloromethane, and we're told that this is a halogen that can be formed by heating a mixture of chloromethane and chlorine. So the first thing we have to do is write an overall equation for the formation of trichloromethane by the reaction of chloromethane with chlorine. So we can see, because they've very nicely given us the formulae here, that we are replacing two of the hydrogens in chloromethane with two chlorines. Now, you wouldn't be asked to do more than one substitution in any sort of single run through of initiation, propagation and termination, but you might be asked, like we are here, to write an overall equation for this process. So we're told we're starting with chloromethane and chlorine, so that's what I'll get down first. Chlorine, remember, like with all the halogens, is diatomic. Now, if we want to make from the chloromethane the trichloromethane, then I need that as my formula, as one of my products. And the, I guess, bit to remember for our overall equation is that the other product that we do make, which is formed in the first propagation step, is always the hydrogen halide, which, because we're using chlorine here, will be hydrogen chloride. And that forms when the hydrogen, the first hydrogen and then the second hydrogen, is removed from our starting material. And then that reacts with the chlorine free radical in that first propagation step, as you'll see in a second, to make the HCl. Now, we need to balance overall equations like this where we have more than one substitution occurring. So we can see that we don't have enough hydrogen here on the right hand side to balance with the three hydrogens we have on the left. So we're always going to be looking to balance the number of hydrogen halide molecules we have. So to make three hydrogens in total, I'm going to need two hydrogen chlorides, and then that gives me a total of 3, 4, 5 chlorine atoms on the right hand side, one here and two there is only 3 at the minute. To make that 5, I'm going to need to put a 2 in front of the Cl2. And that is a pattern that you will spot when it comes to balancing these overall equations. Whatever balancing number you pop here will be the same as the balancing number that comes here. Okay. Then we're just asked to name the mechanism for this formation of trichloromethane. So this is expecting us to know that this is an example of free radical substitution. And for those of you watching this who are in year 12, that probably feels like an easy answer at this point in time. But just to give you a heads up, there are a number of different mechanisms you will cover throughout the remainder of this year and next year, and free radical substitution is one of the mechanisms that a lot of students can forget exists, and I think that's because it's sort of different from other organic mechanisms that you will meet. So that will become a harder question when you have other mechanisms that you are aware of. Now we're going to do the single steps, and now we're going to look at substituting one chlorine atom for one hydrogen, and we're going to be starting with the dichloromethane. So we're assuming that we've already substituted one hydrogen to get to dichloromethane, and then we're going to show the reaction of the dichloromethane with chlorine to then make the trichloromethane. So initiation and propagation steps, they can't change, as it will. We're always doing the same things in initiation and then propagation step 1 and 2. For termination, that's just a combination of any radicals. So there's actually 3 different termination steps for every mechanism that you can write, and sometimes, like in this question, they'll give you a specific thing they're looking for. So they're looking for the termination step that's going to enable us to form a compound with that particular formula. So in this case, we have to be specific, and sometimes you won't have to be. Now, initiation is forming the radicals, because that's going to initiate the chain reaction between the radicals and our starting material. So in this case, we're starting with chlorine. So our chlorine molecule will be split into 2 chlorine radicals, which you can write as 2Cl dot. My personal preference has always been to do it as Cl dot plus Cl dot. And the dot represents an unpaired electron. So when this bond between the chlorine atoms breaks, it breaks equally, and each atom gets an electron back. So this chlorine will again have 7 in its outer shell, so it has 1 unpaired electron, as does this one. This is what we need our UV light for, in case they ever ask that. So the UV light is present as an essential condition to break the chlorine-chlorine bond. And then the first propagation step, again, always following the same sort of series of steps. So in the first propagation step, we always have our starting material, so the dichloromethane. That will always react with a free radical in the first step. And then we will make a new radical, which will have one of the 2 hydrogens here removed. So CHCl2, as one of the carbon hydrogen bonds break, and that leaves us with an unpaired electron on the carbon, and it has to go above the carbon or before the carbon. We can't put it here at the end because that doesn't show which atom the unpaired electron belongs to. So really important that you put it either above or in front when we have an example like that. And then the hydrogen that's been substituted off will react with the chlorine free radical to make the hydrogen chloride, and you will always make the hydrogen halide in step 1. In the second propagation step, we take the intermediate radical we made in propagation step 1, so the CHCl2 with the unpaired electron on the carbon. That then reacts with a new whole molecule of Cl2, and that will then enable us to A, pop 1 chlorine atom onto that radical there by forming a new carbon-chlorine bond to make the trichloromethane that we've been trying to make, and then the other chlorine becomes a chlorine-free radical. And this is why this sort of reaction is so dangerous, because you are always remaking a new radical that can then go into step 1 propagation again. So this occurs in a nice, or not very nice for the ozone, chain reaction, and that's why we ended up with a hole in the ozone layer. So that will then continue to go on and on and on until, in termination, the radicals combine with each other. Now, some students make the mistake of popping a chlorine-free radical in here to then make the desired product, but A, that then doesn't generate this radical to restart propagation, but also if we have 2 radicals combining, that would actually be a termination step, not a propagation step. Now, the 3 radicals that we can be joining together in termination, in this case we've got a Cl radical, we've got the CHCl2 radical, and we can combine either 2 Cl dots, 2 CHCl2 radicals, or 1 of each. Now, if we have to come to create a compound with that formula there, the 2 radicals I'm going to have to combine are the 2 CH2Cl radicals, because that's the only way I'm going to generate a compound that has got, and I've totally written that wrong, 2 chlorines and only 1 hydrogen. So we'll swap the 2's for there, my apologies, pop those out. So yeah, 2 of these radicals here is the only way that we can get 2 carbons into the product of that termination step. Obviously, if we join 2 Cls, we'd just have Cl2. If we joined one of each, we'd make more of our main product, and that only has 1 carbon and doesn't follow that ratio. So it's going to be 2 of those, and then we know what product we're getting, which is the C2H2Cl4. Now, personally, I don't like using molecular formula like this, and we should never be using molecular formula for any of the free radical substitution mechanism steps. And the reason why I don't like it is because from the molecular formula here, we can't tell whether each carbon has 2 chlorines or whether one has 3 and one has 1. So I would prefer to write that. I mean, they've used it in the question, so I'm going to go with what they've used, but I would write it as CHCl2, CHCl2, so as a structural formula. And that goes for all of the propagation steps as well, particularly when we have longer alkanes, because we have to show which carbon it is that is losing a hydrogen and which carbon is then getting the additional halogen atom substituted on. In this case, they've used the molecular formula, so I'm going to follow suit. But if you were just writing a termination step without any kind of particular desired product, I'd like to see structure. If you had got free reign of which termination step to do, however, I probably wouldn't be doing that one. I would be doing one of the easier 2, which would be the reverse of initiation. So 2 chlorine radicals joining back together to make Cl2, or one of the chlorine radicals with one of these radicals to make more of our desired product. I think those are a bit easier. Okay. Moving forwards, we're then told that the chloro-trifluoromethane, the CClF3, chlorofluorocarbon, is used as a refrigerant, but it is being phased out due to concerns about ozone depletion in the upper atmosphere. And in the upper atmosphere, the CClF3 decomposes in the presence of UV light, forming a reactive intermediate that catalyzes the decomposition of ozone. Now, they purposely aren't using the word free radical because they want you to be aware of the fact that the free radicals are the reactive intermediates, and it is the chlorine free radicals that we need to be worried about. So the fact that this CFC contains fluorine, that is not a worry to us. It's the presence of that chlorine atom that is really troubling. So the first thing we have to do is show how from that CClF3 we can generate this reactive intermediate. It tells us that UV light is present, and it tells us that the CClF3 will decompose in the presence of that UV light. Now, the UV light up here was used to break the chlorine-chlorine bond. With CFCs, the UV light is there to break the carbon-chlorine bonds. So we are going to get 1 radical of CF3, where the carbon will have the unpaired electron because it's the carbon-chlorine bond that's breaking, and then that generates our chlorine-free radical. And that is the dangerous part of this whole decomposition. Now that we've done that, the question on the back is asking us to show equations, or to write, equations that show how that chlorine-free radical is involved in catalyzing the decomposition of ozone. And I'll come back to the catalyzing part in a second. So what this chlorine-free radical will do is it will attack the ozone, and we're going to be writing 2 sort of propagation equations here. Now, my advice for these is to learn them, but also if you have an understanding of how propagation steps work, that will help in terms of memorizing them easier, but also if you then forget them, you can kind of sort of piece them together a little bit. So the chlorine-free radical will react with ozone, which has the formula O3. And the first thing that will do is it will take an oxygen off of the ozone to make O2, and then the chlorine-free radical will then form a bond with the oxygen atom that is removed from the ozone molecule to give us this intermediate radical, the CLO dot radical. And just like we did on the previous page for propagation, that intermediate radical then comes forward into step 2. Now here, it's going to attack another molecule of ozone. That's what it's got access to in the upper atmosphere. And that is going to give us 2 molecules of oxygen, because we're going to again lose an oxygen from this molecule of ozone, and then that will bond with the oxygen part of the intermediate radical, and then that is going to regenerate that really dangerous chlorine-free radical, which again can then restart the process and react with more ozone, and that will keep going and going and going until these radicals join together and the reaction is terminated. Now this led to a big hole over the ozone, in the ozone layer, over Antarctica, and it is what got CFCs banned from use. So well done to global scientists for doing that. In terms of why we say that the chlorine-free radical is catalysing the decomposition of the ozone, so obviously catalysts speed up reactions without being used up themselves, we can show that because the chlorine-free radical that we use in step 1 is then being reformed in the second step. So that shows that it is acting as a catalyst, it's not permanently changed. The other thing that we can do for reactions to prove whether something is a catalyst or not is to join the reaction steps together, cancel anything that appears on both sides, and if the catalyst isn't in the overall equation, then it is being a catalyst. If it appears in the overall equation, then it will be acting as a reactant, not a catalyst. So if I was to add these 2 equations together, we'd get a Cl radical on the left, we'd have 2 molecules of O3, and then we'd have this ClO radical as well. On the right hand side, we'd have 3 lots of O2 plus this ClO radical plus this chlorine-free radical as well. And there would be a Cl radical and a ClO radical on both sides, so they would cancel, leaving us overall with 2 lots of O3 going to 3 lots of O2. That's our overall equation. Chlorine-free radical is not in that overall equation, and therefore it's acting as a catalyst. Coming out with those equations is a really common question, so definitely ones to get on a flashcard, or however it is that you sort of go about learning sort of factual information. I'd definitely be doing it with those. With regards to the other parts of this question, that's more of a needing to understand the process, and what I would suggest is practicing writing the initiation, propagation and termination steps, particularly the propagation steps, because the pattern is always the same. Okay? Any questions at all, as always, please let me know, either in the comments of this video, or please drop me an email to missgtutoringandresources@outlook.com. Thanks so much for watching, guys.